population 3 stars are an additional problem for the Big Bang. Did you know that the Big Bang, by evolutionists' own admission, by Big Bang supporters' own admissions, cannot produce anything heavier than lithium? So you get the 3 lightest elements, hydrogen, helium, lithium. All those other atoms on your periodic table, and there are quite a few, if you recall, all of those cannot be produced in the Big Bang. None of them can be. Only hydrogen, helium, and lithium. That's it. So where did all this other stuff come from? Well, the only way Big Bang supporters can think to produce these are inside stars. They say, well, stars then formed after the Big Bang, and those stars made these heavier elements in the core. And that is theoretically possible. It is theoretically possible that stars can produce heavier elements in the core. But if you think about it, if all the heavier elements came from stars, then the first stars would not have had any, right? The first stars that formed after the Big Bang would not have any heavy elements because they're produced in stars. The first stars can't have any. And some of these stars should still be around today. And so we should be able to see what they call population 3 stars, stars with no heavy elements in them at all. And do we see any of these stars? It turns out that every star we know of has some heavy elements in it. There are no population 3 stars, as far as we can tell. And we've got quite a sample to choose from, because there are over 100 billion stars in our galaxy, but none of them have what they call metals, the heavier elements in them. None of them. That's a huge problem if you believe in millions of years in the Big Bang. But it's not a problem if you start from the Bible, the authoritative, infallible Word of God. God made the stars. He gave them the right ratio of elements that He wanted for His pleasure.
Okay, let's start where Jason Lyle is correct, and then move on to where he's wrong. So, he's correct to say that the first generation of stars were made only of hydrogen, helium, and lithium. And this is simply because the Big Bang only made hydrogen, helium, and lithium, and it takes stars to make heavier elements. So, the first stars had to initially be only made out of hydrogen, helium, and lithium. And we call these population 3 stars. This is in contrast to stars like the Sun that are population 1 that have a lot of elements heavier than helium. And then population 2 stars, which are stars that have significantly less of their masses and elements heavier than helium than, say, the Sun. So he's right about that. And he's also right that we've never seen a population 3 star. We've never seen a star that doesn't contain any elements heavier than lithium. But he's wrong to say that we should see population 3 stars today. And he's definitely wrong to imply that this is some big problem with the Big Bang Theory. All right? And I want to explain why. Why it is that we're not expecting to see population 3 stars, even though the first generation of stars were population 3 stars. Okay? Now, the reason why we don't see any population 3 stars today is because they have all died. They've long ago died. All right? Now, to see sort of how this works, let's draw a timeline where we have the history of the universe. So if we have time going this way, then we start at t equals 0 at the Big Bang. Then the first stars form about 200 million years after the Big Bang. And then today, we are 13.799 billion years after the Big Bang. So, now, when a population 3 star forms, it immediately starts making elements heavier than, well, it starts burning hydrogen into helium, then eventually it'll burn the helium into all these other elements. It'll burn helium into carbon, and the carbon into oxygen, and the oxygen into neon, and so on. So, as soon as a population 3 star forms, or at least shortly after, the heavier elements are made in the core of the star. And then when the Pot 3 stars explode, they release these heavy elements into space, they mix with the surrounding environments, and they become part of the next generation of stars because they mix with the gas. Then the gas collapses to make future generations of stars. So the future generations of stars already begin their lives with heavy elements heavier than lithium, and so those were the population 2 stars, the stars that formed after or right after the population 3 stars exploded. So the only time in the universe where population 3 stars are actually being made is 200 million years after the Big Bang. So for a population 3 star to still be around today, it had to have a lifetime, so that it had to have a lifetime of 13.599 billion years, because that's the amount of time that passes between 200 million years after the Big Bang and the present. Okay, so for us to see the Pop 3 star, it has to have a lifetime, like I said, of at least 13.599 billion years. Now, the reason why, the reason why we don't see any population 3 stars is because they all had lifetimes less than 13.599 billion years. Now, that brings up the next question, which is, what determines the lifetime of a star? Well, what determines the lifetime of a star is its mass. Now, we're defining lifetime to be, so stars produce energy by burning light elements into heavier elements. Hydrogen into helium, helium into carbon, and so on. So we're defining the lifetime of a star to start at when it first starts fusing elements, lighter elements. The star begins its life burning hydrogen and helium, and so that's time 0 in the star's life, is when the hydrogen starts burning into helium. Then eventually the fusion will stop because it will run out of stuff that it can burn. Okay, and so that's the death of the star. And so the lifetime of a star we're defining just to be the time between when fusion starts and when fusion stops. And there's different reasons why fusion can stop. It can blow up. The star can blow up as a supernova, but it can also eject its envelope as a planetary nebula and leave a white dwarf behind. But regardless of how a star dies, the lifetime of a star is entirely determined by its mass. And the rule is, the higher the mass, the shorter the lifetime. Now this may seem counterintuitive because because the more massive a star is, the more fuel it has to burn. But the more massive a star is, the stronger the gravitational field that's created by the mass. And pressure is what's opposing gravity in a star to keep it from collapsing. So the fact that stars with more mass have stronger gravitational fields means that you're going to need more pressure to support that star against gravity, and the pressure comes from the energy released by fusion. So the more massive a star is, the greater the rate at which it has to burn or fuse lighter elements into heavy elements in order to provide enough pressure to support the star to prevent it from collapsing under its own gravity. And it turns out that the rate at which as the mass of a star increases, the rate at which it has to burn its fuel increases faster than the rate at which, or increases faster than the mass, so that the total time it takes to go through all the fuel in a star decreases as the mass increases. Okay, so the point is the higher the mass of a star, the more fuel there is, but the faster it has to burn the fuel to support it against gravity, and it just happens that the rate at which the fuel is burned increases faster with mass than the amount of fuel, and so the total lifetime of a star decreases as the mass increases. And we can, in fact, write an approximate expression for the lifetime of a star in terms of its mass. And this is approximate, but the lifetime of a star is approximately equal to 10 gigayears, times the negative 2.5 power mass in solar masses. So this m sub o dot, m sub circle dot is the mass of the sun. So this is very rough, but it tells us the age of the lifetime of a star in terms of its mass. In the negative exponent means that higher mass, shorter lifetime. So if a population 3 star, for a population 3 star to still be around today, its lifetime has to be 13.599 billion years. So we can sort of invert this equation to find what is the mass of a star whose lifetime is 13.599 billion years. So if you were to solve this for mass, you would get mass equals solar mass times T over 2 years to the negative 0.4. So this is just writing the mass in terms of age or lifetime. So now if you plug in the 13.599 billion years into this, you get a mass of 0.884 solar masses, which means 0.884 times the mass of the sun. So any star, any population 3 star that has a mass greater than this will have a lifetime less than 13.599 billion years. It will not be around today. And if its mass is less than that, then its lifetime is greater than 13.599 billion years, and then it can still be around today. So the explanation then for why we don't see population 3 stars today is that they all had masses greater than 0.884 solar masses, and therefore lifetimes less than 13.599 billion years, and therefore they've all died. So that just brings up the next question, of course, which is, what determines the mass of a star? Why were population 3 stars so massive compared to the stars that form today? Well, that brings us to the question, what determines the mass of a star? Well, remember that stars form from gas clouds that collapse under their own gravity. Okay, so you have, the basic idea is you have some gas cloud in space, and normally it doesn't collapse because there's a pressure gradient force which balances gravity. So you have it gets more dense towards the center and less dense as you get away from the center. So the highest pressures at the center, and then the pressures decrease. And so what that does is that the change in pressure, there's always a force between high and low pressure. So the fact that the pressure is highest at the center and then decreases towards the edge means that there's a pressure gradient force that points at every point in the cloud. There's a pressure gradient force that points directly away from the center of the cloud. Now, in addition to that, there's the gravity. Every molecule in this gas cloud is attracted to every other molecule by gravity. Now, of course, the force between any two molecules is negligible, but the net force, the net gravitational force on one molecule by all the other molecules in the cloud is not negligible. And in fact, the net force always points towards the center of the cloud. So you have, in addition to the pressure gradient force which points directly away from the center of the cloud, and then you have the gravitational force which points directly towards the center of the cloud. It's the net force due to all the molecules. Okay, and now normally they're going to be in some sort of balance. If they exactly balance, are set equal. Now, for the gas cloud to collapse into a star, something must happen to cause the gravitational force to be greater than the pressure gradient force at each point in the cloud. And the way that happens in practice is The main difference, a big difference between gravity and pressure is that you can get rid of pressure, but you can't get rid of gravity. Gravity is created by the mass of the gas cloud. The mass of the gas cloud, it doesn't change; it's constant. So the gravity, you can't get rid of gravity, but you can get rid of pressure. The pressure is coming from the random motions of the atoms in the gas cloud, right? So they're just moving randomly, and the higher the temperature, the faster they're moving, and the higher the pressure. So to get rid of the pressure, or to decrease the pressure, you can do something to lower the temperature. And you can lower the temperature by radiating away the thermal energy. Okay, so any object that has a finite temperature will emit thermal radiation. So this cloud will emit thermal radiation, and thus it will lose its thermal energy, and thus its temperature will decrease with time, and the pressure will decrease with time. And eventually, the pressure gradient force will no longer be able to balance the gravitational force, and it will collapse into a cloud. Now, there's an exact criteria that must be satisfied by the cloud in order for it to collapse into a star. And that has something to do with something called the Jeans criteria for instability. And it works something like this. If you have So you have your gas cloud, and it has three important properties. It has a temperature, the temperature, then it has a mass density, and it has a mean molecular weight, which is basically the average mass per molecule. Now, given these three numbers, you can calculate a quantity called the Jeans mass. And there's an explicit formula for it. All right? So the Jeans mass is defined to be, or the Jeans mass, the formula for the Jeans mass is this, well, there's a bunch of constants. The square root of pi to the fifth, Boltzmann's constant cubed, temperature cubed, and 36 on the denominator, g cubed rho, Newton's constant cubed, mass density, and then mean molecular weight cubed. All right, so that's the Jeans mass of a gas cloud, and most of these are constants, so we often just say that it's proportional to the 3/2 power of temperature, the negative 1/2 power of density, and the negative 3/2 power of mean molecular weight. So here's what this means. If the mass of the cloud is less than the Jeans mass, then the cloud is stable against gravitational collapse, and it won't collapse into a star because pressure can support it. But if the cloud has a mass greater than the Jeans mass, then it will collapse into a star, or at least it will begin to collapse. I mean, it will collapse. Whether or not it makes a star is more complicated, but if the mass of the cloud is greater than its Jeans mass, then the pressure gradient force cannot balance gravity. Gravity is stronger, and it will collapse. So the way that you should picture this is you have a cloud in space, and it has some density and mean molecular weight and temperature. Okay, and you can imagine that the density and mean molecular weight are constant, but the temperature is dropping as the cloud radiates energy into space. The temperature drops, and therefore the Jeans mass drops because the Jeans mass goes to the 3/2 power of temperature. Okay, now, so you start with the cloud. You start with the cloud having a mass less than the Jeans mass, so the cloud's stable, and then it radiates energy, and its temperature drops. As the temperature drops, the Jeans mass drops, Eventually, the Jeans mass is going to drop below the mass of the cloud. And at that point, the cloud will collapse into a star because there's not enough pressure to support it against gravity. All right? So gas clouds collapse into stars once their mass is higher than the Jeans mass. And the Jeans mass has this formula here. Now, not all of the gas in the cloud actually makes it into the star. Typically, about 30% does, because as the star forms, it's going to generate stellar winds and radiation and stuff, and that's going to exert a pressure. That's going to push outwards on parts of the cloud and prevent it from becoming part of the cloud, prevent it from becoming part of the star. And so only about 30% of the mass ends up. There's also outflows and stuff, but only about 30% of the cloud, the gas, makes it into the star. So the mass, basically the main point is the mass of a star is about 30% of the Jeans mass of the gas cloud that it collapsed from. Okay, so remember what we're trying to do is we're trying to explain why it is that population 3 stars had masses greater than 0.88 solar masses. Okay, so it must be because the Jeans mass of the gas that the first stars formed from is higher than, something like 2.94 solar masses. I mean, the point is, remember that the mass of the star is 30% of the mass of the Jeans mass. So if the Jeans mass is 2.94 solar masses, then the mass of the star that forms from it's 0.88 solar masses. So we have to, in order to explain why there's no population 3 stars today, it must be the case that the Jeans mass of the gas that the first stars formed from is greater than 2.94667 solar masses. Now, so in a gas cloud, the mass density and the mean molecular weight are not that important for determining the Jeans mass because they don't vary much. What is important is the temperature. It has the temperature. The Jeans mass varies as the 3/2 power of the temperature. So, if the gas clouds that the first stars formed from had the same mass density and mean molecular weight as the gas clouds today that form stars, then the only way we can explain why the Jeans mass of primordial gas is higher than the Jeans mass of like gas of the Milky Way would be that the temperature of the primordial gas is higher than the temperature in the Milky Way. So before I move on, I want to show you what the Jeans mass is in the Milky Way. So we observe stars forming from gas clouds in the Milky Way that have the following parameters. First, the temperature. Most gas is not able to collapse into stars, but the stars form from these gas clouds that are called dense cores, and they have a temperature that's very cold, 10 Kelvin, and they have a mass density of about something like 10 to the negative 18 grams per cubic centimeter. And a mean molecular weight like 2.4 hydrogen masses. Hydrogen mass of 2.4 times the mass of the hydrogen atom. Now, if you plug these numbers into the Jeans mass formula, you find that the Jeans mass is something like 0.477 solar masses. And then if 30% of that becomes a star, then a typical star mass, a typical mass of a star that forms in the Milky Way would be like 0.143 solar masses. All right, and that's correct. I mean, that's a typical stellar mass. A typical mass of a star that forms in the Milky Way is something like that. So, if primordial gas was just like gas in the Milky Way, it had the same parameters, temperature, density, and mass, then we would not be able to explain why we don't see population 3 stars, because the population 3 stars would have a mass of 0.143 solar masses, and so they would have a lifetime greater than 13.599 billion years, and they'd still be around today. So in order to explain why we don't see population 3 stars, we have to explain why these parameters were different for primordial gas than for gas in the Milky Way. Now, if we're assuming that the density and mass is mean molecular weight's the same, then the only thing that can be different between primordial gas and the gas that in the Milky Way is the temperature. So, for population 3 stars to not be around today, the temperature of the gas clouds that the pop 3 stars form from must be much higher than 10 Kelvin, so that the gene's mass is much higher than this. So that brings us to the next question. What determines the temperature of a gas cloud? Well, there are processes that heat a gas, and there are processes that cool a gas. And the temperature is set by equating the two. The temperature is the temperature such that the heating rate equals the cooling rate. Now, in the Milky Way, the heating processes are, for a gas cloud that's becoming a star, there's 3 or 4 different things that heat the gas. First, there's the fact that it's collapsing means that you're compressing the gas, and compressing a gas heats it. So that's one heating process. That's one thing that heats the gas. Then, in the Milky Way, there's cosmic rays, which heat the gas. And then if there's stars nearby, then they can emit energetic photons, which heat the gas. Or if there's a star, once a star forms in the middle, it's going to emit its own photons and heat the gas. Okay, so cosmic rays, compression, and a little starlight, whether from within or from without the cloud. Those are things that heat the gas. In the primordial universe, there are no cosmic rays, because cosmic rays come from supernova, and there are no, we're talking about the first stars, so there are no stars yet. So the only thing that can heat the gas, the only gas heating process is compression. As gravity makes the cloud compress, it heats up. So that's the only heating source for the primordial gas. Now, what about the cooling? The only way that a gas can cool is by emitting thermal radiation. And remember how this happens. The way that a gas emits thermal radiation is, and I discussed this in the previous video, is you have 2 atoms that collide. Okay? And during the collision, some of the energy of the colliding particles goes into the atom, goes into one of the atoms to bring it to an excited energy state. So there's a collision, and then one of the atoms is in an excited state. The electrons are the electrons in the atom are at a higher energy level, or the other one's not. Then, to get to the lower energy level, the excited atom emits a photon. Right, so if it emits a photon, then it can go back to the lowest energy state, which is called the ground state. Okay, and this is how a gas emits thermal radiation. It's just atoms collide. One of them goes into an excited state, takes the energy, some of the energy of the colliding particles, and then emits a photon, and that carries away the energy that was captured during the collision. And so this is constantly happening in the gas. Photons are constantly being emitted, and the gas is emitting thermal radiation. Now, before moving on, I should say that atoms are not the only thing that can participate in radiative cooling. You can also have molecules participate. Okay? And the way that works is, if you have a molecule, then so a molecule has electrons, just like atoms do, and those electrons have quantized energy levels. But molecules also have energy associated with rotation and vibration. Okay, so if you have a molecule, it can rotate. Or vibrate. And the energy associated with the rotation and vibration is quantized, just like the energy of the electrons are. So there's a set of, each molecule has a set of electronic energy levels, which are then divided into a set of vibrational energy levels. And each vibrational energy level is then split into rotational energy levels. So the total ground state of the atom, of the molecule, is going to be the ground state where the molecule is in the lowest electronic level, and the lowest vibrational level, and the lowest rotational level. And so then a molecule can participate in radiative cooling basically just like an atom does. You have a molecule, it collides with an atom, and the molecule gets sent into a higher rotational or vibrational state. And then to get to the ground state, it emits a photon. All right, it's the same basic idea. It's just instead of electronic energy levels, it's rotation and vibration. Now, each atom and molecule has its own set of energy levels. And it's that set of energy levels that determines how cold a particular atom or molecule can get the gas, how much it can lower the temperature. All right, and let's sort of see why. By drawing the energy levels of hydrogen, the hydrogen atom. Okay, so we have, if we define the ground state as energy, if we define the ground state to have ground state is probably n equals 1, and we'll define its energy to be 0. Then the first excited state has an energy of 10.2 electron volts. Okay, an electron volt is a unit of energy. Then the third excited state, or the second excited state, has an energy of 12.1 electron volts, and so on. Okay, now in the gas, most of the hydrogen atoms are going to be in the ground state, and they can only go to the first excited state if they collide with another atom, and the center mass kinetic energy of the colliding particles is large enough. It has to be at least 10.2 electron volts, because if you want to get the hydrogen atom in the second energy level, it has to, from the first energy level, it has to gain 10.2 electron volts of energy. So only collisions between hydrogen atoms and something else where the colliding particles have at least 10.2 electron volts of energy can result in the hydrogen atom going to the first excited state, and then of course it can drop to the ground state by emitting a photon. But 10.2 electron volts is actually very large. there aren't that many atoms in a gas that have that much energy at normal temperatures. And in fact, for hydrogen atoms, the temperature has to be at least 10,000 Kelvin for there to be enough atoms for there to be enough hydrogen atoms moving at 10.2 electron volts to actually to do this thing where they go to the second energy level by collisions and then drop to the first level by emitting a photon. So hydrogen atoms can only cool a gas to 10,000 Kelvin. You can start at some high temperature, then the hydrogen atoms will emit photons and the temperature will drop, but it will stop dropping at 10,000 Kelvin because once you get there, there just aren't enough hydrogen atoms moving fast enough to do this thing and participate in radiative cooling. So hydrogen atoms can only cool a gas to 10,000 Kelvin. Helium atoms are even worse. They have an even larger spacing between the ground state and first excited state. So now in the Milky Way, the gas gets down to 10 Kelvin, and that's because the Milky Way has carbon and oxygen atoms and CO molecules and dust grains, and they have much closely spaced energy levels. So, for example, if you take a look at the energy level of a carbon atom, then the first excited state has an energy of 0.002, 0.04 electron volts. So that's a very close spacing. That means that carbon atoms only have to be moving with an energy of 0.002 electron volts in order to participate in radiative cooling. And in fact, that's such a low number that even at 10 Kelvin, there's enough carbon atoms moving that fast to participate in radiative cooling. So, and then oxygen atoms and CO molecules and dust grains have similar or even finer spacing. So you can get in the Milky Way, you can get gas cold because it has these atoms and molecules that have very finely spaced energy levels, so that it doesn't take that much energy to have them go to the higher energy level and then drop down. But the primordial gas only had hydrogen, helium, and lithium. And there wasn't enough lithium to participate in radiative cooling. It's insignificant because there's only one lithium atom for every 10 billion hydrogen atoms. So the only possible coolants of the gas, the primordial gas, is hydrogen and helium. And we've just seen that hydrogen and helium have such large energy spacings between the ground state and the first excited state that they can't cool a gas below 10,000 Kelvin. Now, if this was, if this was the problem, if this was an insurmountable problem, so that you could not get the gas below 10,000 Kelvin, then this is unacceptable because the gene's mass at 10,000 Kelvin the gene's mass at 10,000. The gene's mass at 10,000 Kelvin is, for the same density and mean molecular weight as the Milky Way, is 17,136 solar masses. Okay, and 30% of that, which is what the star would be if it was formed from that, is 5,140.8 solar masses. Now, the problem with this is that's too high. You can't have stars that massive. You can't. If there was a gas cloud that actually had these parameters, and a mass greater than its Jeans mass, then it would collapse into a black hole. It would not collapse into a star because it would have so much mass that there would be no way to make hydrostatic equilibrium. Okay? Now, this is great if you want to make the seeds to primordial black holes, because this is the sort of thing that, at the center of galaxies, there's these supermassive black holes, and they have to start somewhere. And a good way to make a seed black hole that could grow into a supermassive black hole would be to take something that's a gas that's 10,000 Kelvin and have it collapse. Once it becomes gravitationally unstable. But that's not good for making stars. We need to make stars. And to make stars, you need to have gas that has a Jeans mass that's way less than 5,000 solar masses, or 17,000 solar masses. So how do we get the gas cold enough to make stars if the only atoms that we have that can cool the gas are hydrogen and helium atoms, and they can only cool the gas to 10,000 Kelvin, which is not cold enough to have a star. Okay, I think I'll continue. I'll explain that in the next episode.